Okay, welcome back. So now we've gone from 2 repulsions to 3, so things are going to get a little more tricky here. So let's start with something, like CO3 2 minus. So that's a polyatomic ion, and if you remember, that's the carbonate ion. And I'm going to go ahead, I'm going to draw out the Lewis structure for this. So the Lewis structure looks something like so. And the thing's got a charge. I guess I should go ahead and put it in square brackets, right, and write the charge next to it. So now I'm going to look at the central atom here. So the central atom, right, is this carbon here, and I'm going to ask how many things are repelling directly connected to it. So any kind of bond, any kind of lone pair is going to count. So what do I have here? Well, I've got a bond over here, and I got a bond over here, and I got a bond up here. And remember, double bond just counts as any kind of bond. So double or triple, they're all treated the same in VSEPR. So I've got 3 repulsions here. And the question is, how do 3 things try and keep apart from each other? And I'm going to go ahead and pull up that PhET website again, and let's take a look together. All right, let's try and build that carbonate ion. So what did we have? We have a single bond on one side, a single bond on the other side, and a double bond on the third side. So I can kind of move that around, and you can see that they're staying away from each other pretty well, right? If I try and sneak up and try and move the atoms around, no matter what I do, right, I end up with that same kind of geometry. So let me go ahead and rearrange that. So we've got that kind of that 120-degree triangular shape, and if I click the show bond angle button here, you can see here that each one of these is 1/3 of a total revolution, so 120 degrees. And if I line them up side on, you can see that all the atoms lay flat in a plane. So this whole thing would sit on your piece of paper that you're writing these notes on, and nothing would sit up in the air, nothing would bump down into the paper. And if I click in the lower left-hand corner on molecular geometry, it tells me the name is trigonoplanar. All right, so let's redraw carbonate's Lewis structure. So on the page, it looks something like this. And okay, lots of lone pairs. And we said before, right, that there are 1, 2, 3 things repelling here. And we've seen that when 3 things repel, they take this triangular planar, trigonoplanar geometry. So I'll go ahead and write that in my untidy writing on the side. So trigonoplanar, that is the name of the geometry. And notice I've drawn it out with those bond angles. Those bond angles are all 120 degrees. And what do we have at the end of those bonds? At the end of those bonds are oxygen atoms. And I guess technically that's a double bond, so we should draw it something like that. So that would be the drawing of the geometry of the carbonate ion. So it's trigonoplanar, and it's got that 120 degree. And notice our Lewis structure, we kind of draw it as right angles, but on the page when we show the VSEPR geometry, so the 3-dimensional geometry, we can do a little bit better, right? We're going to write it out as a 120-degree angle, something like so. All right, let's have a look at one more thing with 3 repulsions, and then we'll see that things are actually a little more interesting. All right, so here's something else with 3 repulsions. This is sulfur dioxide. And sulfur dioxide has this Lewis structure here that sometimes trips people up because it's a double bond on one side and it's a single bond on the other side. So it looks kind of lopsided, I suppose. Now, if we go ahead and we count the number of repulsions, so we got a single bond here, so that's one thing. We got a lone pair on the top, so that's the second thing. And we got a double bond over here on the left, so that's the third repulsion. So we've got 3 things repelling here. So I can quickly sketch out that 120-degree angle here. So let me go ahead and write it down here on the bottom. And let me put the atoms in. So here's an oxygen over here. Here's an oxygen over here. Technically, it's a double bond. And up here is a lone pair. So I'm just going to go ahead and draw that out. And technically, we can only measure the angle between bonds, actually. We can't really measure the angle between bonds and lone pairs. So you can draw them if you want to, but realistically, we can only measure the angle between the atoms themselves. So this is a 120-degree angle. All right, now this is where the going gets interesting because this geometry actually has 2 names. And the 2 names are either the molecular geometry or the electron pair geometry. And the electron pair geometry is where the electrons are. So this is the geometry where the electrons are. And what that means is that when we've got lone pairs, we include that. So we've got kind of that trigonoplanar shape here. So the electron pair geometry is called trigonoplanar. So what about the other geometry? Well, the molecular geometry, actually, whenever we refer to geometry, what we normally always mean is the molecular geometry. So this is the one on the exam when I say, what's the shape of the molecule or what's the geometry? This is the one I really mean. And this is where the atoms are. And so since the atoms are hard and heavy and have almost the entire mass of the molecule inside of them, we care more about those. The electrons, remember, are about 2,000 times lighter than the lightest atom, and that is hydrogen. So the electrons themselves are kind of fluffy. It's kind of like the air, it has mass, but it's very small. And, compared to your body, which is where most of the mass of you is. So where the atoms are is the name of this geometry. And if we look at where the atoms are, we can see the atoms are lined up, not in a straight line, but they're kind of in this bent shape. And so we actually refer to this geometry as bent. And let me go ahead and pull up that fat side again and try and build that molecule for you and show you again what that looks like and can manipulate it a little bit better than my line drawing. So, okay, let's try. Okay, so I'm going to build this molecule. I'm going to add a single bond, a double bond, and a lone pair. And I love the shape of this lone pair, right? It looks just like a balloon here. And that's why I like to bring balloons to class normally when I do this. So I can move them around with my finger. And if I kind of put the lone pair on the top, then you can see this kind of looks like it did before, right? It kind of looks like trigonal planar with those 120-degree angles. And if I click on the Show Bond Angle button, you can see there's 120 degrees. And if you're wondering, well, what about the other 120-degree angles? Technically, practically, experimentally, you can only measure the angle between the atoms, the bonds themselves. So you can't actually see the lone pairs. We just kind of infer that they're there. And if we click in the lower left-hand corner, we can see the electron geometry. And remember, so far, right, we've been looking at the electron geometry, where the electrons are. And the electrons are still in that same trigonal planar arrangement as before. But if we look at where the atoms are, that's called the molecular geometry or just geometry. And if I click on that, we can see that it's that bent shape there. So those atoms there are not all in a straight line, right? If I try and line them up, you can see that I always get one off to the side. And if I try and line up, the other way around, I'm not very good at this. Okay, and then you can see that they never quite line up straight, so there's no way to get them in a line. I mean, you can get them temporarily in a line, but they just bounce right back again to that 120-degree angle.